Okay, so this next section, we're still talking, like I said, about graphs and their functions, but we're going to get a little bit more into describing what the graphs look like or what kind of graph they would be. We'll talk about like intervals, which just means like where does the graph increase, decrease, where does it stay the same. We'll talk about deciding if a function's even versus odd and like how to actually do those stuff or do those kind of things. The first thing I'm going to go over with you guys is intervals, which we've done intervals before on number lines, like when you guys were graphing in the last chapter, those number line problems, and then you had to kind of state where your solutions were. You would write like parentheses, brackets, you would say it's between these two numbers, or it goes to infinity, or negative infinity, whatever. So we're kind of doing that again, but we're looking at the picture of a graph. And so we're kind of describing like what's the domain doing. So all of these intervals here are mainly talking about your domain. And remember from last week, the domain is your x values of your function. So what are all the x's that belong to this graph? What are they doing? Now, to find your intervals, graphs can do three things. They could be increasing, they could be decreasing, or they could be constant. Some graphs do all three, some graphs only do one, some graphs do two. It just kind of depends on what the function is and kind of what it's doing. So down here on this example, we have this graph over there on the right-hand side of the screen. It kind of goes up and then down, and then it goes back up again. If you can kind of look at the graph and like notice, okay, it went up, it kind of dipped down, it went back up again, that's going to help you see where is it increasing versus decreasing. Because if a graph is going up over time, that's going to be an increase. And if a graph is going down, that's going to be your decrease. If the graph stays the same, like it flat lines out, that's going to mean that it's constant. When you read a graph, you read it like a book, left to right. So you start on the left and you watch, like, what is it doing? And that's how you describe it via intervals. Now, they already have the increasing one done for you. They're saying that it increases from negative infinity to negative 1. So notice that the graph down there, it doesn't end. It just has an arrow that's symbolizing it's going to go on forever and ever and ever down there. So as the graph continues to go left on your x-axis, it goes down. But if you go left on your x-axis forever, you're going to get to negative infinity. But then as it kind of comes up, if I kind of trace it here, they say that it's kind of changes its direction at negative 1. So this is why that first interval is increasing, because it's going up and then it kind of takes a turn. It goes down at negative 1 for a little bit. Where does it turn back the other direction? At like 1. So like right here. So this part of the graph that I kind of went over there in blue would be our decreasing interval, because that's the area where it's going down. So to write that, we would say it started to go down at negative 1 to positive 1. And then it starts to do what again? Increase again. And it starts to go up at 1 and it goes forever. So we would write 1, comma, infinity. Because again, as the graph goes to the right, it continues to go up. Now, this one had no constant intervals. There was no time where the graph like flattened out, and that's okay. This one just increases and decreases. Now, normally, like in the future, I would start to combine like my increasing ones together. Like I would just put those on the same line. I maybe wouldn't write it out separately like that. But it is okay if you need to do that, just so you can kind of follow the path of the graph. Why don't you guys try the second one? Write down where you think, is it increasing, decreasing, is it constant? So was the graph increasing anywhere? If so, where was it increasing at? Okay, negative infinity to negative 2. That takes care of like this part of the graph right there. And then what happens? it's constant for how long? Okay, so that takes care of this part. And then what happens? Starts to increase again? To 2 to infinity. So what I'm going to do is back up where I had an I for increasing. Underneath that, I'm just going to write 2, comma, infinity. But if you wrote it down below constant, you wrote another increasing or I for increasing, that's fine if you kept it separate. Does that make sense, everyone? Okay, so if we turn the page over, another thing that we can look for on graphs is something called relative maxima or minima. This would also be known as like the maximum value or the minimum value. So what's the highest point that the graph appears to hit and the lowest point? Now, most graphs don't end, so they do eventually go either to positive or negative infinity, but we can't measure that. We can't measure infinity as a point. So when they talk about relative, they mean like on the area that we can actually see on the graph, what's the highest and what's the lowest point. It doesn't mean that it's the truest, like lowest point of the graph. But again, if a graph goes forever to infinity, how do we measure that? Because we can't measure forever. So when I look at this graph, do you guys kind of see how there's 2 points highlighted on it? Like a red dot and a blue dot? That's trying to show you what they're talking about here, like maxima and minima. So relative maxima would be the highest point that the graph seems to hit, which would be where that red dot is. And we have to kind of estimate where we think this would be because the graph doesn't have all the numbers on the y-axis labeled. It's going by fives, so just be aware of that. About where do you think it is here? Probably 3. So I would write that maxima as -1, 3. And then how would you guys write the coordinate for that blue dot? -2 maybe? I agree. I don't think it goes quite all the way down to -3. I think it's a little bit higher or closer to the axis than that red dot is. Okay? But yeah, that's all you're really doing when they ask for max and min. You're just trying to describe those high-low points that you see. Okay. Next thing I want to talk to you guys about is symmetry. Symmetry is when you can draw a line through something and it looks the same on both sides. You spend a lot of time in geometry talking about symmetry and like line symmetry, rotational symmetry, and those kind of things. Graphs can also have symmetry depending on if it's an even or it's an odd function. So we're going to kind of switch into that now, and I want to talk to you guys about how do you tell if something is an even function versus an odd function, and what does that mean as far as its symmetry. So we're going to start with even functions. The big idea I'm going to highlight here is that a function is even if it does this. Okay, if you have the function as it is, so like you just kind of look at the equation, and if you take the x values and you change the sign of them, so if you change whatever you're plugging in to the negative, or if it's already negative, you change it to the positive, then what that's going to do is it's going to keep it the same. If they equal the same amount, that means that your graph was even. If they don't equal out to each other, then it's not an even function and it doesn't have that symmetry. If a graph is even, so I'm going to highlight this too. If a graph is an even function, it's symmetric to the y-axis. That means that the y-axis is acting like that line that can cut your graph in half. Probably the most common graph that you guys know that would be an even function is a quadratic. Okay, so remember quadratic graphs are y equals x squared. Okay, all quadratics are going to be symmetric according to the y-axis, but let's kind of just talk about why. If I put in a number, I like to think about it with numbers sometimes because when we get too involved with letters, it can get really confusing. So let's think about numbers. If I plugged in a 2 for the x, it would look like this. 2 squared. What would you get? Y equals what? 4. Let's imagine if I switched the 2 to the opposite sign. So if I put in a -2 instead, what do you get? Still 4. See how when I plugged it in, I got the same answer both times. That's what makes a function even. If you can plug in the positive side and the negative side and you get the same answer twice, that means that you're dealing with an even function. If it's even, that means that the y-axis is a line of symmetry. Now let's talk about odd functions. Odd functions are a little different. So if you are looking at putting in a negative value for your x, so kind of think about like what we did with the even. If we flip the sign, if it's not even, then we're going to test to see if it's odd. So you always start with the even function test first. If it satisfies, then you're done, because it can't be both. It has to be either even or odd. It can't do both things. So if it's not even, then we would compare it to, okay, well, what if I look at that negative, like the opposite case, and if I compare that to just taking the entire function and making the whole thing negative. So notice how they put like a minus sign in front of the f of x. So instead of just making the x term negative, they're making the entire function negative. So that means any other numbers that maybe are showing up in your graph too, or in your equation, would have to switch signs. If they're equal to each other, then that tells you that it would be an odd function. And so the graph of an odd function, if it's odd, is going to be symmetric to the origin. Origin, remember, is just a point, 0, 0. So that would be when you put in a number for the x value, and it does switch. Okay, so let's take again a look at this one. This is a graph of a cubic function, which is y equals x to the third. If I was going to start this, I would compare it first to even. Okay, so I'm just going to do the whole thing. Like if I was testing this to be an odd, I would have first started out, is it even? So let's just again start with a number. Let's do 2. If I put 2 in for x, what would this get? 8. Okay, if I was testing for it to be even, then I would say, okay, what if I change 2 to negative, and then I raise it to the third power? What's negative 2 to the third power? Negative 8. Okay, are those the same? No, so this tells me that it's not even. Okay, if it's not even, there's a chance then that it would be odd. So then what I'm going to do is I'm going to think of it like this. Y equals negative 2 to the third. Notice how I put the negative on the front, not in the parentheses. I'm checking to see if I make the whole equation negative, is that going to equal what we just got? So if I do 2 to the third, that's still 8, but now there's a negative out front. And so I get negative 8. So since these two things match, that's what tells me that it's odd. So when you're doing these kind of problems and you're trying to decide if it's even or it's odd, you always start by testing for even first. Because if it's a yes for even, you don't even have to think about testing it for odd. Because if it is even, it can't be odd. Now, if it fails the even test, you will have to check it for odd. If it still fails the odd test, then it's neither. Because there are some graphs that don't have symmetry at all. All right, so let's practice this again. This time I'm not giving you guys a graph. I'm just giving you a function and we want to decide, is it even, odd, or neither? Okay, so we're starting out with this function here. It says h of x equals x to the fifth plus 1. The first thing they did is the even test. Okay, so even is when we take the x and we make it negative. So I'm just going to try to highlight this here. They changed that x from the x to the fifth to a negative x. That's really the only difference that we did there. And when they change that to a negative, it causes that x to become negative x. Again, if you think about putting in a number here, it's raised to the fifth power. So even looking at that exponent, is 5 an even number or an odd number? It's odd. So it's probably not going to work out for us to have an even function here because of that 5. It doesn't necessarily guarantee that it's odd, but when you look at that exponent, if it's not an even number, it's probably not going to be an even function. So the 5 causes that x to stay negative, which does not match the original function. Like these two things are slightly different, mainly because of the x value. So it's not even. So then we go on to check to see if it's odd. And again, they're kind of showing you this here is showing you that it fails the test for even. And that's what we have to compare it to now when we test it for odd. So then look at what they did for odd. We had a negative here, and there is a typo here in your guys' notes. Right here on this parenthesis, there should be a negative right there. So like right in front of those parentheses, you need a negative there. So try to squeeze that in there. Because now if you look, there's a negative out front of the parentheses. If you distribute that in, you get negative x to the fifth. And then the 1 also has the negative attached to it now, so it becomes minus 1. So this is what we need to compare it to. Do these two things here match? No, they're still different. So that means it's not odd either. So this is actually not either one. So it's not odd, which means it's neither. Those ones just kind of showed you with working with the function. We didn't have like any numbers put in for x. Again, if it's confusing, put in a number for x because it helps like look at just a number instead of looking at a whole bunch of letters. Questions on even versus odd? Okay. We're going to switch gears a little bit here and talk about piecewise functions. Piecewise functions are when you have a graph that's maybe made up of more than one equation. So even when we were describing on those first couple of problems from today, if something was increasing versus decreasing versus constant, if a graph is doing a bunch of different things like that, it's because it's made up of a bunch of different little pieces. Because otherwise a graph would be doing the same thing or it would have some kind of pattern to it. So piecewise functions kind of represent those graphs that have different intervals happening. And again, we've done this before. This is something that you guys would have done last year in Algebra 2. They're giving you this function up here at the top, and just kind of notice how it's written. It's got like two different parts to it. It says 3, comma, x is less than or equal to negative 1. This is like one part of the function. And then the bottom says x minus 2, comma, x is greater than negative 1. So we're going to split these apart into two different like tables. This is how I always kind of just break them apart is I make two small tables for these and I try to evaluate them at the points and I use the inequality that they provide me with to know what points I need to use. The other thing we'll want to look for is does it have an equal sign with the inequality because that tells us if we start our graph with an open or a closed circle. So we're going to start with this first one, which was 3 when x is less than or equal to negative 1. That number, if you remember, is the number that you start with. So you're going to start your graph at negative 1. And that first one, does it have an equal sign with the inequality? It does, right? Because it says less than or equal. So what I like to do is right next to that on the table, I like to just draw a little closed-in circle to remind myself when I go to graph these points, it's going to start out with a closed dot. And then for my rest of my numbers here, I want everything that's less than or equal to negative 1. So what are some numbers that are smaller than negative 1? Negative 2, negative 3, and negative 4. Now look at the equation that they gave me. It's just 3. Do I have anywhere for the x's to go? It doesn't say like 3x, it just says 3. So when you don't have somewhere for x to go, your answers are just that number. So this is just going to be all 3's. Okay, and that last column, you can fill it out if you want to. I'm not going to just because this is where you would write your coordinates. I think you guys are able to just use those numbers and now graph them. So I'm going to come over here to my graph. We're going to go to negative 1, 3, and there's going to be a closed circle. So I always make that first point a little bit bigger than the rest of them. And then the next point is at negative 2, 3, negative 3, 3, negative 4, 3. You guys should hopefully see that it's a flat line going to the left. So you're going to start at that closed circle and you're going to draw your line going to the left. Okay, Okay, so now let's do the second part of this function. What's the inequality say for the second half? X is what? Greater than -1. So again, we start at -1. This time, no, does it have an equal sign? No, so it should be an open circle. What numbers are bigger than -1? Yeah, 0, 1, and 2. Now this time, we do have an x. The equation says x minus 2. So we're taking all of those numbers minus 2. So what's -1 minus 2? 0 minus 2. Keep going. Good. Now, if your graph starts to get, like, the functions start to get crazy, guys, use your calculator. Use the table function on your calculator to type those little pieces in, and then you can go straight to your points. You don't even have to type it all in if they start to get really complicated. Again, I'm not going to write out the ordered pairs. You can if you want to. I think you guys are beyond that point. So -1, -3, this time have an open circle. Don't fill it in. Then 0, -2, 1, -1, 2, 0. So this one appears to kind of be going up to the right. Any questions on the piecewise function like that? All right, we've got one last thing to talk about. So stay with me here for another couple minutes. On the last page, they want us to find and simplify a function's difference quotient. Okay, so difference means subtraction, and quotient means division. So we're subtracting a function and we're dividing. So there's kind of a combination here. The expression that we use looks like this. Okay, on the top, it says f, and then your original function would have just been x. But they're adding an h to it, and then you're subtracting the function, so that's where the difference comes in. And then it's all over h, and that's where the division happens. So we're going to do two examples here. One is kind of already written out for us, and then we're going to do one from scratch. So this first example, I'm just going to kind of talk you through, and hopefully you can kind of follow along here. But this is the function that they're giving you. So that's what we're going to use to do this whole process too. The first thing that we need to do is figure out what is the function when I add that h to it. So when I change my equation by putting in an h. That means for every x you see in your equation, you now have to add h to it. And that's what they're doing in this step here. They have the -2, and then instead of just x squared, notice how it says parentheses x plus h, because they're adding in that h, and then that whole thing is squared. And then the second x now becomes x plus h, and then we still have plus 5. When you square that x plus h, you'll have to expand it out. So it becomes a binomial. This is really x plus h times x plus h. And that's how they get this piece here, is they FOIL that. Everything else, though, you really can't do a ton with until now. When we kind of bring everything down, we start to combine like terms. So they distribute that -2, and then we get this whole big mess here. But if you can combine things, you should do that. So what they're showing you underneath here now is that after you did this x plus h piece, like this whole quantity goes right there, because that's just from my expression up here. That's that first kind of chunk. Then there's a minus sign, and you bring down the function f of x, and then notice how it's still all over h. That's just coming from the equation that I started out with. Then what they're doing is they're simplifying. They're trying to combine like terms that they see. So what they did is they brought everything down. They did distribute this negative over here to get those last three terms to all change their signs. And then we start looking through here, and I start to notice that there's some things that are going to cancel off right away. Like there's a -2x squared and there's a positive 2x squared. So these cancel. There's a positive 5 and a -5, so those cancel. There's a positive x and a negative x. So you start to be able to eliminate a lot of things. But now I think we're kind of stuck. There's nothing else that I can just cross off. So they drop all that stuff down. The last thing they did here is they noticed that all those terms on the top have an h. And so they factor that out. And then those h's the one from the top and the one from the bottom cancel. And so this is your answer that they're asking for when they talk about the difference quotient. So let's do one from scratch. Nothing is done here. Let's start by doing the f with x plus h. So in for your x's, I want you to replace it with x plus h. So where it says x squared, we're going to write that as x plus h squared. And then we have plus 3. And in for this x, we're going to write x plus h. And then minus 2. Now, earlier, when I showed you guys this problem up here, they already did that x plus h for us. It was right here. It's what I underlined in blue. Do you guys see what I'm circling again? So guess what? You get to use it again. You don't have to redo that every single time. It's going to be that same quantity over and over and over again anytime we square it. So I'm going to rewrite this as x squared plus 2xh plus h squared. For that second quantity, let's distribute the 3. What would it say if I distribute 3?
3x plus 3h.
Yep, 3x plus 3h, and then we have minus 2. Okay. Then what I'm going to do is start to add on the other stuff. So this is like the first, like that's just the f plus h piece. Then we have to subtract the original function. And then it's all over in h. Okay, now it looks like a mess right now, but at this next step, this is where we're going to start to be able to cross things off. So I'm just going to drop everything down from that first piece. It just says x squared plus 2xh plus h squared plus 3x plus h minus 2. On that second set, because we're subtracting it, we got to distribute the negative. So it's going to switch those signs, and that's how we're going to start to get things to cancel. What can we cancel off?
H.
We're not quite ready to cancel off h yet.
Do the x squareds,
X squareds are gone.
the 3x, and then the 2.
Good. So you should get rid of quite a few things up there, and you should be left with 2xh plus h squared plus h.
Yeah, I thought it was 3h.
Oh, did I miss a 3?
Because you're distributing 3.
Oh, yeah. Yep. Thanks for catching that. That would have caused us a problem in about 30 seconds. That should be a 3h right there. Okay, all over h. Then we can factor out an h. And that's still all over h, and then eventually they cancel off too. And so you're left with just the 2x plus h plus 3. So it's a little bit of a mess there. It's not hard math. I mean, it's just you got to keep track of all your things. But eventually stuff should start to cancel off. Okay?